In this class, we're going to talk about digital colour. We deal with colour every day. We work with colour, we have colour all around us. But when it comes to actually putting numbers on colour, digitising colour, that's a bit more complex. We've already seen how black and white images can be digitised. It's easy to see that one shade of grey can be lighter or darker than another. And we can set up a scale with black on one end, white on the other, and all of the intermediate shades of grey in between. And then we can assign a colour, a shade of grey. We can assign it a particular value depending on where it fits on that scale. So grey is easy. It's a simple question of how bright something is. But colour is more complex. Two colours could be equally bright and still be very different. So there's a bit more going on there. So in this class we'll think about what colour is and how to put numbers on it. Digitisation is, after all, just a question of assigning numbers to things, expressing things in numerical form. So we'll be asking the question, how do we put numbers on colour? So to understand colour, we have to understand light. Although we deal with light every day, very few of us actually understand what light is and how it works. The visible light that we see every day is part of the electromagnetic spectrum. Now, it's hard from our everyday experience to grasp that the light that we are seeing is exactly the same thing that's emitted from a radio station, the same thing that cooks food in our microwaves, and the same thing that's in X-rays. So the electromagnetic spectrum is very large, and with our eyes we can see just a tiny portion of this. So the reds, yellows, blues, oranges that we see every day, they're just a small part of the electromagnetic spectrum. Beyond that, we have things like X-rays, radio waves, gamma rays, microwaves. We can see certain frequencies of light with our eyes. We can see between 43,000 and 750,000 gigahertz. However, it's more common to talk about the wavelength of visible light. Frequency and wavelength are related by this equation here. C equals Fw. C is the speed of the wave, and in this case it's the speed of light. F is the frequency of the wave, and then W is the wavelength. So using values we already have, we can calculate that the wavelengths of visible light are between 400 and 750 nanometers. So red light has a wavelength of about 700 nanometers. Yellow has a wavelength of about 590 nanometers. And light with a wavelength of 500 nanometers would be blue. So one way we can characterize colour is based on its wavelength. We could have a scale that ranges from violet through green and yellow all the way to red at the far end. We could then assign a value to the colour based on where it is along this scale. This value is known as the hue. All of these red colours here have the same hue. These blues have the same hue. All these greens have the same hue. And these yellows all have the same hue. So categorizing colours by hue is the same as assigning them a value based on their position in the rainbow. And that's a very natural way to go about it. But it turns out the rainbow doesn't have all the colours we're used to having every day. There's no pink, black, grey, for example, in the rainbow. So it turns out there's more to colour than hue. Now consider this cup of hot chocolate here. It's brown. And after I add some milk, it's still brown, but it's not the same brown, it's paler. Now what has changed here is the saturation of the colour. And the more milk I add, the paler it gets, and the lower the colour saturation. So when the saturation is high, the colour is very strong, and when the saturation is 0, the colour is grey. Now, these blues here all have the same hue, but their saturation levels are different. Here we can see different saturation levels for this red. So saturation refers to the purity of the colour. Pink, for example, is red with low colour saturation. Now, hue and saturation together are not enough to account for all the variations in colour that we see every day. Consider these colours here. They all have the same hue and saturation. What makes them different is their brightness. Now, we're on familiar territory here when we're thinking about brightness, because that's what we measured when we looked at coding black and white images. Brightness is a measure of the amount of light. So when you adjust a light with a dimmer switch, for example, you're adjusting the brightness. So with hue, saturation and brightness, we need 3 different values to describe a colour. When starting out, it can be difficult to get to grips with the hue, saturation and brightness and how they interact. Most computer programs let you specify a colour using the hue, saturation and brightness values. Now, using these is a good way to actually see how the system works. This colour picker is from an Apple program. You can adjust the hue, the saturation and the brightness separately. Hue is generally considered to be a point on a circle, and so is one of 360 degrees. Saturation and brightness are percentages. 100% saturation is pure colour, 100% brightness is a bright colour, and 0% brightness is black. Here's another colour picker from Apple. Here the hue is shown as a circle, and moving clockwise or anti-clockwise around the circle will change the hue. At the centre of the circle, the saturation is 0, so colours close to the centre have low saturation. At the outer areas of the circle, the saturation is high. The brightness is controlled by a separate slider there along the side. Adobe Photoshop also has a colour picker. Here the hue is controlled by a slider on the right. At the top of the square, the brightness is high, and at the bottom it's low. And then at the left of the square, the saturation is low, and at the right of the square, the saturation is high. Experimenting with colour pickers can really help your understanding of hue, saturation and brightness.